Samsung's chip division just shipped a stack of glass wafers into one of the most secretive supply chains on the planet, and it isn't going anywhere near a graphics card. Leaked schematics show it's headed towards something Apple has never let outside engineers get close to. But the part nobody is talking about isn't the glass itself. It's the one product Apple is deliberately keeping this material away from. And by the end of this video, you'll understand exactly why that decision is on purpose, not an accident. Copper became the standard inside computer chips in the late 90s when IBM figured out how to wire transistors together with it instead of aluminum. Copper carries a signal with less resistance, which means less wasted energy and less heat for the same amount of work. For almost 30 years, that single decision held up the entire chip industry. But here's where it gets complicated. The thing actually failing right now was never the copper wiring itself. It's the platform underneath it. Picture a highway system. The copper traces are the roads, and the substrate underneath is the ground those roads are paved on. For decades, that ground was built from an organic resin, similar to a hardened plastic, chosen because it was cheap, moldable, and good enough for a single slab of silicon sitting quietly in the middle of it. That worked fine when a chip package held one piece of silicon. But modern AI chips now cram a dozen separate chiplets onto a single package, all wired together through that same plastic base. Under heat, that plastic base warps. Not much. Fractions of a millimeter. But at the scale these chips operate, fractions of a millimeter are enough to crack a copper trace, misalign two chiplets, or short an entire connection. Engineers have spent the last few years fighting this with tighter tolerances and better adhesives. All of it is engineering workarounds for a material problem, and the workarounds have run out. Here's the number that proves it. Modern AI chip packages need interconnect lines thinner than 5 micrometers. A human hair is about 70 micrometers wide. You are routing electrical signals through gaps 14 times thinner than a strand of hair on a foundation that physically moves, under heat that would melt a kitchen stove. At that scale, the difference between a substrate that holds its shape and one that drifts even slightly is the difference between a chip that works and a chip that doesn't. So the industry didn't need a copper replacement. It needed a floor that doesn't move. And that floor is glass. A sheet of semiconductor-grade glass stays flat under heat in a way plastic never will, which means engineers can draw copper traces on top of it far closer together than on organic material, roughly 10 times the interconnect density in the same physical space. Not 10% more, 10 times more. To connect layers vertically, manufacturers laser drill microscopic holes straight through the glass, called through-glass vias, and fill them with metal. That's harder than it sounds. A Chinese company called Sky Semiconductor has already shipped more than 20,000 units of wafer-level packaging using this approach, and in the process achieved a 4-micron via diameter breakthrough, later mastering 2.5D high-density glass interposer technology for large chip AI, CPU, and GPU packaging. 20,000 units isn't a lab demo. That's a production number. Meanwhile, Guangdong Fozhixin Microelectronics has been building out its own panel-level fan-out and glass substrate processing lines in Foshan, working on the same problem from a different angle. None of this comes free, and being honest about the cost is part of why this story holds up. Glass substrates still run roughly 2 to 3 times the cost of the organic material they replace, and glass is physically brittle in a way plastic isn't. A microscopic crack from laser drilling can sit invisible for weeks and then fail months later under thermal stress. Corning, the same company behind the Gorilla Glass on your phone screen, has already put close to $900 million into semiconductor glass packaging research, specifically because the defect problem, not the underlying physics, is what's standing between glass and mass adoption. Every serious player in this race, American, Korean, Japanese, Chinese, is chasing a solution to that same crack problem at the same time. And that's the part almost nobody frames correctly. Because while everyone assumes this is a Western-led race, the numbers say otherwise. BOE, the same company that makes the display in half the phones on Earth, has been quietly building toward this since 2020. It invested 390 million yuan in 2022 to build a wafer-level innovation platform compatible with both glass and silicon substrates, then nearly $1 billion yuan more in 2024 to construct a panel-level glass packaging substrate pilot line. 6 weeks ago, in a formal investor filing, BOE disclosed that the pilot line had achieved fully automated equipment integration, with a design capacity of 1,000 substrates a month, and full process control over through-glass via drilling, deep copper filling, build-up layer deposition, and circuit patterning. Every step, end-to-end, domestic. BOE has already sampled 20-layer, high-density glass core substrates to domestic customers, some of which have moved past proof of concept into technical testing. Here's the honest caveat. because this is where most coverage either oversells or undersells the story. 1,000 substrates a month is not a supply chain, it's a beachhead. TSMC's advanced packaging operations process tens of thousands of wafers a month. Absolute scale production of glass substrates for AI chips doesn't exist yet anywhere. Not at BOE, not at Intel, not at Samsung. Intel has been developing glass substrates since 2023, with mass production targets stretching toward the end of the decade. Samsung's component division has its own mini glass substrate line targeting 2027. And on American soil, a company called Absolix, a subsidiary of Korea's SKC, broke ground on a $600 million glass substrate facility in Covington, Georgia, and received $75 million in direct CHIPS Act funding specifically to build that plant and keep this manufacturing layer from concentrating entirely overseas. So the race genuinely is open. But here's the structural advantage nobody talks about. BOE has spent 30 years building large-scale precision glass manufacturing for displays at a volume no Western company touches. That equipment knowledge, that glass handling expertise, that supply chain already exists. BOE isn't starting from zero. It's extending a capability it already owns into a far more valuable product. And on the equipment side, China's Hans Laser is already delivering domestically produced through-glass via laser drilling systems. China isn't waiting to buy this equipment from anyone. It's building it. Here's why the timing matters right now and not 5 years from now. The newest generation of AI memory, HBM4, needs a connection more than 1,000 bits wide to the processor sitting next to it, moving over 2 terabytes of data every second. Fitting that many connections into that little space requires through-glass via density that organic substrate simply cannot hit without warping apart. HBM4 is sampling now, with volume production targeted for this year. That's not a future problem. That's this year's problem. And 3 weeks ago, the market noticed. On June 17th, glass substrate stocks in China surged dramatically in a single trading day, with multiple companies hitting their daily price ceiling at once. That kind of move doesn't happen by accident. It happens when TSMC sends a CoWoS glass substrate development plan to its own supply chain, signaling that the world's most important chipmaker is formally committing to this transition. When TSMC moves like that, every supplier, every investor, every competitor takes it as confirmation that the timeline is real. Now here's the geopolitical layer, because this is where the chip war story goes somewhere most people haven't followed it. The entire Western semiconductor containment strategy for the last 5 years was built around one choke point: lithography. Specifically, the extreme ultraviolet machines made by ASML. No ASML machine, no advanced chip. Export controls were built around that single dependency, and for that specific path, the logic holds. But glass substrates are a completely different path. You don't need an ASML machine to make one. You need glass expertise, precision laser drilling equipment, and manufacturing know-how. None of which is export controlled, none of which is on a restricted list. The wall built around one layer of the chip does nothing to the layer sitting right underneath it. So here's the obvious question. If glass substrates are this close, why isn't your next iPhone the thing proving it? Because it isn't going into the iPhone at all. And that's not an oversight, it's a decision. Leaked schematics from a supply chain breach earlier this year show the iPhone 18 Pro's A20 chip is moving to something called wafer-level multi-chip module packaging, or WMCM, which fuses the processor and memory at the wafer level before they're even diced apart, instead of stacking them on top of each other the old way. That's a real, heavily leaked change. Better heat dissipation, wider memory bandwidth, less thermal throttling. It is not glass substrate packaging. It's the stepping stone toward it, not the destination. The actual glass substrate hardware Apple has its hands on right now is going somewhere else entirely. Samsung's component division has reportedly been shipping glass substrate samples to Apple, and Apple is said to be running its own independent testing separate from its partners. Something Apple rarely does this early in a technology's life. But the target isn't your phone. It's a chip reportedly codenamed Baltra, built alongside Broadcom on one of TSMC's most advanced processes, destined for Apple's own AI data centers, the ones running private cloud compute. The entire point of Baltra is cutting Apple's dependence on Nvidia's GPUs for its own AI workloads, and Broadcom is already lined up as one of the largest customers for Samsung's glass substrate business. None of that touches your phone directly, but it changes what your phone can do. Every time your iPhone quietly hands off a hard AI computation to Apple's servers instead of running it on device, you're leaning on exactly this infrastructure. Denser, cheaper server packaging is what makes those features fast and free instead of slow and metered. And here's the twist. Because Apple avoiding glass in your pocket isn't a limitation. It's the smartest possible decision. Glass is still brittle. still prone to microscopic cracking during drilling and cutting, still years away from surviving the abuse a phone survives, drops, hot cars, being run through an airport scanner every single day. A cracked substrate in a data center rack gets swapped out overnight by a technician nobody ever sees. A cracked substrate in an iPhone becomes a viral video and a lawsuit. So Apple is doing the one thing that actually makes sense, pouring its riskiest, least proven material bets into the products with the least public exposure and keeping the most battle-tested packaging in the device you're holding. That's not a delay. That's a firewall. And that firewall matters more than it sounds like, because of who's building the glass on the other side of it. China now has companies working almost every layer of this supply chain at once. BOE on the glass core, Substrate itself, Sky Semiconductor and Fozhixin on through-glass via manufacturing, Hans Laser on the drilling equipment that makes it possible. That's not one breakthrough company. That's an entire parallel industry standing up at the same time the West is still finishing its first pilot lines. Washington already sees it coming, which is exactly why Absolix got that $75 million in Georgia, a direct attempt to keep this layer from concentrating entirely overseas. Nvidia sees it too. Just weeks ago, Nvidia put over $3 billion into Corning, and Intel committed a similar amount to a glass substrate facility in India. Everyone serious is trying to lock in a position in a layer of the chip supply chain most people watching AI headlines have never even heard of. If glass substrate becomes the default packaging layer for AI chips, the way organic substrate was for the last 2 decades, whoever controls the manufacturing at scale isn't just selling a component. They're sitting underneath every AI accelerator on the planet. Nvidia's, AMD's, Apple's, everyone's. And unlike the export controls dominating headlines around the processor itself, there's no equivalent ban stopping Chinese firms from selling raw glass substrate material into that same global supply chain. Here's the question I actually want your answer to, not the easy one. The bottleneck strategy behind export controls worked because it correctly identified lithography as the single choke point for advanced chips. But glass substrates prove that strategy has a blind spot. A parallel path that requires none of the controlled technology, built on capability China spent 30 years developing for a completely different industry. Does that mean the bottleneck strategy is fundamentally flawed, or does it just mean it needs to expand to cover more of the supply chain? Those are two very different conclusions, with two very different policy implications. Tell me exactly where you land in the comments. I read every reply on this channel, and this is one of the debates I genuinely want to see develop. If you want to track shifts like this before they show up in mainstream headlines, Iron Circuit is the channel that finds them first. Subscribe and turn on notifications, because the next video covers exactly how Nvidia is quietly restructuring its own packaging supply chain in response to this glass transition. And the number that comes out of that story is the one that should change how you think about why your next graphics card costs what it costs. I'll see you there.